In this video, we're going to solve some problems from the book involving the matrix representations of linear maps. Some where we're just finding the matrix representation, and another one where we'll find the matrix representation and use that to solve the problem. So first, here's problem 3 from the book, where you have a linear operator L on R3. Remember, an operator means that it's going from R3 to R3 again. And we're just using the standard basis here. So just 1, 0, 0, 0, 1, 0, and 0, 0, 1. And we're going to find the matrix representation of these three linear operators. So let's just start with A. Remember, all we need to do is we need to put in our basis vectors. So the first basis vector is 1, 0, 0. Technically, it's a column vector that we're plugging in here. And we'll see what vector we get out. Now, our formula here is that the first coordinate is x3. x3 here is 0. Then our next coordinate is x2. Well, x2 in this case is 0. And then finally, we're getting x1 as our third coordinate. x1 in this case is actually 1. So our output is 0, 0, 1. And we do this for the other two basis vectors as well. And hopefully this is not too hard to see what happens in this case. So first one is x3, which is 0, then x2, which is 1, and then x1, which is 0. And finally, x3 is 1, x2 is 0, and x1 is another 0. So for this particular case, our matrix representation, where these are the columns, maybe I'll just go ahead and write that over here, matrix A, and it doesn't want to write, there we go, matrix A. The first column is 0, 0, 1. Our second column is 0, 1, 0. And our third column is 1, 0, 0. If we take this and multiply it by x1, x2, x3, we will get the column vector x3, x2, x1. Next, we do the same thing for the L of part B. In fact, we'll just write down the exact same thing for this first part. So we have L of 1, 0, 0, L of 0, 1, 0. And then L of 0, 0, 1. And we need to figure out what each of these three vectors are. In this case, our first vector, we take x1 for our first coordinate, so x1 is just 1. Then we take x1 plus x2, we have 1 plus 0. And then finally, x1 plus x2 plus x3, 1 plus 0 is again a 1. For our second one, now we have x1 is this 0, x1 plus x2 is 1, x1 plus x2 plus x3, well 0, 1, 0, add the 1, so we get 0, 1, 1 for that vector. And then finally, we take x1 is 0, x1 plus x2 is another 0, x1 plus x2 plus x3, we're going to get a 1. And notice that these are the columns, so we need to write them down as columns and not as rows. So we have our first column is 1, 1, 1. Our second column is 0, 1, 1. And our third column is 0, 0, 1. And again, if we take this matrix and multiply it by a column vector x1, x2, x3, we will get exactly this formula for our column, for our resulting column vector. And finally, for C, starting again the exact same way. So this is a pretty algorithmic type process. You just kind of crank out the same process every time. In fact, once you get used to this, you can kind of skip writing this down and just directly just think about, well, what if I put those in there and just write down the columns? But here we're gonna write them all out explicitly so that we can demonstrate the point. Okay, in C, the first one, 1, 0, 0, if we put those in here, well, x3 is 0, so we get a 0 for that first spot. x2 plus 3, x1, well, the x2 is 0, x1 is 1, so we get a 3 there. And then finally, 2x1, so 2 times 1 minus 0, that gives us a 2. We do that for 0, 1, 0. So again, x3 is 0, so we get a 0 here. Then x2 is 1 plus 3 times 0, so we get a 1. And then finally, 2 times 0 minus 0 is just 0. I don't know why it sometimes works well and sometimes it doesn't. Finally, we have 0, 0, 1. This time x3 is not 0, so we do actually get a 2 for that first spot. Then we have 0 plus 0, so we get a 0 here. And finally, we have 2 times 0 minus 1, so we get a negative 1. And again, we need to make sure that these are our columns. So our matrix A has first column of 0, 3, 2, second column of 0, 1, 0, and third column of 2, 0, negative 1. And just to reiterate the point, this is the matrix that you would multiply to any vector of the form x1, x2, x3 to get exactly this formula for the result. Now we're going to skip to problem 18. So I wanted a problem where we actually are using different bases for our RNs, but we're still just looking for the matrix representations. So here we're working with maps from L is going from R3 to R2, but R3 has the basis E, which is given up by U1, U2, U3 with these formulas, and R2 has the basis F. It has basis of B1, B2 that are given by these formulas. We want the actual matrix representations of these three maps using those bases. Now, one thing to note here is that we will be using the transition matrix for the basis F, which means that we're just going to take the matrix where we use the B1 and B2 as our columns. And keep in mind, our transition matrices are always going to be square matrices. So if you get something that's not square, well, you weren't working with a basis, or you're trying to work with the wrong dimension. And of course, using our formula from before, we do need the inverse of this matrix. Now, the determinant of this matrix is not too hard. Just 1 times negative 1 is negative 1, but then we subtract 2 times negative 1. So we have negative 1 plus 2, we get 1. The determinant of 1 makes this really easy. So we actually would be dividing by the determinant if it weren't anything other than 1. And then we use the adjoint method. Well, that just means that we're going to swap these two. So we have a negative 1 here and a 1 here. And then these two, they'll actually stay where they are, but they'll get a negative. We'll get a negative 2 here, and we'll get a positive 1 there. This is our inverse matrix. And we're going to end up multiplying this to all the matrices that we get from our process of plugging in our basis vectors. So the process after we've actually found this transition matrix will be very similar to what we did in problem 3. We are going to take our L and we're going to plug in vectors. But this time, instead of plugging in 1, 0, 0, 0, 1, 0, and 0, 0, 1, that standard basis, we are going to plug in these u's. So L is going to have 1, 0, negative 1 plugged in. Then we're going to take 1, 2, 1, plug it in. And we're going to take negative 1, 1, 1, and plug that in and see what we get. We're going to do that for the other two problems as well, but we'll just work with A for now. Of course, these are technically column vectors. We'll go ahead and put our T just to stress that point. And what we're going to get is actually just two numbers over here. So our first formula, our first coordinate is x3. So the third coordinate here is negative 1. And then x1, so we take that 1. So our first one is negative 1, 1. Then we have 1, 1. It's really nice when we have these very simple formulas. And then finally we have 1 and negative 1. We're going to take these and we're going to put them into a matrix. These are our columns, remember. So negative 1, 1, 1, 1, and then 1, negative 1. But this is not our matrix representation. We're going to have to take this thing. Actually, I probably should have written it a little further over. So let me move this. And then we are going to take this matrix and we're going to multiply it by B inverse. So we have negative 1, negative 2, 1, 1. We have to multiply it on this side. Then we'll just, what is this product? That will be our matrix representation. We just take rows by columns like we normally would do. We're going to get negative 1 for this first spot, negative 3, 0, 0, 2, and 0. And hopefully I don't have to walk through all the matrix multiplication. You know how to do that by this point. But this is the matrix that if we multiply it by the coordinates of a vector, so if we take a vector x, which is x1, x2, x3, but we put it into terms of this basis here, which may be convenient for a given problem that we might be working on later. Not in this class, but maybe in some cases that'd be something we might want to do. Then we could get coordinates of the result in terms of just multiplying it by this matrix. Part B, we do exactly the same kind of thing. We are going to go ahead and just plug in the same vectors, the same basis vectors of our basis E. And see what we get. So here we have x1 plus x2. We just add these first two components. In fact, let's just do that for all of these right now. So 1 plus 0, 1 plus 2, negative 1 plus 1. Those are our first components. And then we have x1 minus x3. So we're going to take our first component minus our third component. So 1 minus negative 1 will give us a 2. 1 minus 1 is 0. Then negative 1 minus 1 gives us a negative 2. And those are going to be our columns. Now, of course, we are going to have to multiply that by B inverse. Then we write down our columns and work out this product. This product is going to be a matrix representation. And in this case, it's going to be negative 5, negative 3, 4, 3, 3, and negative 2. Just multiplying those two together. And we do exactly the same thing for C. So kind of a tedious thing going through each one of them over and over again, but this is how we learn. We just practice until we can't figure out how to forget it anymore. We plug those vectors into our new L. L of x is 2x2 comma minus x1. So we're going to take, well, our first component is going to be 2 times our second component, so this one's going to be a 0, this is going to be a 4, and this one's going to be a 2. And then we're going to take our first components, we're just going to put a minus sign in front of them. So 1 becomes -1, -1 again, and then now this is a positive 1. And then we just multiply by b inverse again, where our columns are now 0, -1, 4, -1, and 2, 1. To get a matrix representation of 2, -2, -3, -1, 3, and 3. Finally, we're going to take a look at an earlier problem, so problem 14. This is a problem where we are not looking at Rn to Rm. We are going to look at two vector spaces that are different. In this case, P3 and P2, sort of like we had in our simpler example back in our last video. But we're going to make it a little bit more complicated. We're going to go ahead and keep the standard basis of x squared, x and 1 for P3. I know they put these in brackets, but I don't really like doing it that way. They just use the brackets to note that these are in a particular order. We cannot change the order of those. So this is our standard basis for P3. That's easy enough. P2, on the other hand, is going to use the basis 2, 1 minus x. And you could go and actually test that is a basis for P2. Every linear map, so anything of the form mx plus b, can be written down in terms of these two basis vectors. Might have to use some fractions, but we can do that. Our map, this L that they give us here, is we put in a polynomial, we get out the derivative of that polynomial, and then we add what we'd have if we plugged in 0 to that polynomial. So we'll see how that goes as we do this. Now note that this question is not really asking what is the matrix representation of this linear map. They are actually asking us to find the coordinates of these particular vectors, or the coordinates of the images of these particular vectors in our basis for P2. We are going to do that through using a matrix representation. And we'll see how having a matrix representation can actually allow you to do all this, do repeated problems like this with a little bit more ease than having to go through and doing them all directly. So the first thing we're going to do is find a matrix representation. Remember, that means we are going to take our basis vectors in P3. We're going to plug those into our linear map. So here we want to take x squared, the polynomial x squared, because that's our first basis vector. We are going to take the derivative of x squared, so that's 2x. And then we need to add whatever we get when we plug 0 into the function x squared. So 2x plus 0. Almost feels like we don't need that part, but it will come into play a little bit later. Now we need to figure out what is this 2x in terms of the basis 2, 1 minus x. Because we're not dealing with 2, 0 as we would have if we were actually using the standard basis. No, we're actually going to have to put this into a new basis. And we want to make sure that we are working with the correct ordering on this basis as well. So what do we have here? Well, the only one that has an x in it is the 1 minus x. So to get this 2x, we're going to have to take this, and we're going to have to multiply it by -2. So take -2 times 1 minus x. But those aren't equal, because this also contributes a -2. We need to get rid of that somehow. Well, how can we do that? Well, we can just add 2 to it. add 2 to it, or more specifically, we're adding 1 times the basis vector 2. So if we write out 1 times 2 minus 2 times 1 minus x, that will give us 2x. And so what are the coordinates of this? The coordinates of L of x squared in the basis of, or did they give it a name? They didn't give it a name. Let's call this f, because that's what we've been calling the basis on our image. So the coordinates of this vector, of this 2x, is actually 1, negative 2, because those are the coefficients of these basis vectors of 2 and 1 minus x in that particular order. So 1, negative 2. Technically, it's a column vector. Let me separate these. We're going to have to repeat this for x and for 1, because those are our other two basis vectors. So what's the derivative of x? Well, it's just 1. What happens if we plug 0 into x? Well, we just get 0. So we only get 1 as our result here, but we do need to put that into the basis of 2, 1 minus x. Well, that's easy enough. All we need to do is take 2 and divide it by 2. So our coefficient here is 1/2. And then we don't have to have any contribution from 1 minus x. I'll write it out here just to be a little bit more clear about it, but this, if we multiply all this out and add them together, we're just going to get the 1 that we expect. So have some fractions here, but that we have to have the fractions there. The actual coordinates are going to be unique. These are the only coordinates that we could have for this particular vector. We'll take 1/2 and then 0. And so, again, a column vector. Finally, we get to just take our vector 1. What's the derivative of 1? Well, it's 0, but we do now actually have a non-zero part for p of 0. So plugging 0 into the function 1 still leaves a 1. So actually, technically we get the same result as when we plugged in x. So we actually get the same coordinates. So 1/2 times 2, and then no contribution from 1 minus x. And so the coordinates in terms of f are 1/2, 0. So what is our matrix? Our matrix is literally just take these 3 vectors as our columns. We have 1, negative 2. We have a 1/2, 0. So 2, not a 3. And another 1/2, 0. Alright, so let's go ahead and actually apply this matrix representation to these vectors. And keep in mind that we have to think about what these vectors are in terms of the standard basis. We're using the standard basis for P3. So in the first case, we're going to take our matrix A, and we are going to multiply it by the coordinates of x squared plus 2x minus 3 in their standard basis. Remember, x squared is our first vector, x is our second vector, and 1 is our third basis vector. So this has coordinates of 1, 2, negative 3. If we multiply those together, well, our first, we have 1 times 1 plus 1/2 times 2, then minus 3 times 1/2. 1 plus 1 minus 3 halves is going to give us a 1/2. Then we have negative 2 times 1, and then zeros here. Those zeros are going to save us a lot of work. We just take that negative 2 times 1 to get negative 2. These are the coordinates of the vector that is the image of this particular vector here. So you can actually say this is the coordinates of 1/2, times 2 minus 2 times 1 minus x in the basis of f. And you could simplify that and actually work out and see that that is correct. For b, we do the same kind of thing. And just keep using the same a with all its fractions and all. But now we have to think about what is x squared plus 1 in the basis of x squared, x, and 1. Well, there's no x in here, so that just means that we have a 0 for that middle spot. But then we have 1x1, or sorry, we have 1x squared and 1, 1. We go ahead and multiply those together. 1 times 1 plus 0 times 1 half plus 1 times 1 half. So 1 plus a half is 3 halves. And then again, 0 is helping us out. We have negative 2 times 1 to give us a negative 2 here. And again, we could go ahead and write this out as what polynomial corresponds to. But the question was to find out these coordinates. C, we do the same thing. Take that matrix A. We're going to multiply by the coordinates of this vector. So this vector only has the x coordinates, or the x vector in it. So we have 3 times 3 in that second spot, but then we have zeros in the other two. So this one's not going to be fairly easy, because we don't have to, when we multiply this out, we have zeros times everything in the first and third columns, but then we multiply everything in the second column by 3. We get a 3 halves and a 0. And finally, D. Same process. I keep making my 2's look like 3's. Sorry for that. So this time, our vector is 4x squared plus 2x. We don't have a linear term, or sorry, we don't have a constant term, so that is a 0, but then we have a 4 and a 2. Then we're going to take 4 times 1, so 4 plus 2 times 1 half, so we add a 1 to it. So we're going to get a 5 here, and then, well, I should have mentioned this before, but the 0 times the 1 half doesn't, it just goes away. And then finally, the negative 2 times the 4 is going to give us a negative 8. And that's all there is to it. Once we have that matrix representation, it's just a matter of doing the matrix product, which is just, you don't even have to think about it. You just kind of crank out the numbers, just do all the adding and multiplying, and you just get your answer. So, very handy for if you need to do a bunch of calculations of the same linear map, and you don't really want to have to think about it every single time. So, okay, hopefully that gives you a good idea of how this thing works, and how we basically have turned the concept of what a linear map is into just all the stuff with matrices that we were working with before. This is why we spent so much time with matrices. They really did come back in a very big way right here. So, I'll see you guys in the next section. We'll talk a little bit more about this kind of stuff, and we'll actually look at, well, if we do have our matrix representation in a particular basis, can we change that basis? We kind of saw that a little bit when we proved the theorem about how to actually find the matrix representation for Rm to Rn, or sorry, Rn to Rm in bases other than the standard basis, but we'll look at it a little bit more generally. So, see you guys next time.